Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is how to perform primary injection testing with the Megger SPI 225. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Daniel Carreño, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Volney Naranjo, Senior Applications Engineer, and Sanket Olar, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Daniel.
Thank you, Michael, and hello to everyone joining us in today's session. As Michael said, we're going to talk about how to perform primary injection tests with the Megger SPI 225, which is a unit that is the latest generation of primary injection units from Megger. Again, we're going to focus today's session on how to perform the test. But as an introduction, I want to just have some level ground in case we have attendees that are just starting learning about these tests. Some introduction on low voltage circuit breakers, nothing too deep. If you want to know more about those, I highly encourage you to look at both past and future webinars in our webpage. We have covered this topic, again, the theory part on circuit breakers, why to test in detail. So again, focusing on the testing itself today, looking at the primary injection method, what it is, how it is performed, and more specifically, how the SPI 225 will help us test in the field, how the features of the unit and its capabilities will help us overcome those challenges that are typically encountered when performing these measurements in the field. So starting with low voltage circuit breaker, right? And with answering the very basic question of what a circuit breaker is, right? We can say that it's a mechanical switching device that will be capable of making, carrying, and breaking currents under normal circuit conditions, but most importantly, also to break currents under specified abnormal circuit conditions such as those of short circuit. It will be the only switching device in the power grid that will be capable of breaking those current under those abnormal conditions, right? Therefore, are indispensable switching devices in the power grid, in the power system. In terms of classification, again, without going too deep, without going into the types, quenching media, and all that, very important for this presentation to make the distinction of low voltage circuit breaker, medium voltage, and high voltage, right? The low voltage circuit breakers, typically considered below 1000 volts, have a very important difference compared to medium and high voltage breaker. And that difference is that the mechanisms for or that the circuit breaker uses to trip, to operate, to break those currents under those abnormal conditions are integrated into the circuit breaker itself, as opposed to medium and high voltage breakers that will need that extra part of or element in the circuit breaker, right? The control section, which will receive external signals to trip or close or to do any operation needed. So that distinction is very important and is the reason that we use primary injection to test these breakers, right? So I will cover that a little bit more in detail in a couple slides. So now that we know what a circuit breaker is, what are the main requirements, right? What do we expect from a circuit breaker when it's installed in the system? First of all, it has to be a very good conductor when it's in the closed position, when normal circumstances, when our system is under normal circumstances, right? In other words, contact resistance will be very low or as low as possible, right? It has to be a good conductor under normal conditions. When it's open, it has to be a good insulator, right? It has to be able to transition fast enough from closed to open or vice versa, especially, you know, on the open operation or the trip operation as we commonly call it. While performing those operations, it's important that it doesn't cause any transient voltages and that it should be able to withstand faults. Additionally, we want or we expect that those operations are performed in a reliable manner. The circuit breaker must operate immediately, even after long idle times and under any possible climatic condition. In other words, we expect a very good both electrical and mechanical endurance from the circuit breaker. And speaking of which, right, on the other hand, how do these elements of the system fail, right? The mechanical parts are prone to corrosion, fatigue, broken parts, misalignments, hardened grease, dust, or low temperatures. The current carrying parts, the conductors, prone to loose connections, thermal overstressing, or short-circuit events, right? The other elements, right, we can have miswire sensors, incorrect settings, or solid-state devices, like electronic trip units that can be dead or shorted or programmed incorrectly. The graph that you're showing, that you're looking at right now, is from the nuclear industry. It was published by EPRI. And even though again is from the nuclear industry, it's a good representation that tells a very good indication on where the majority of the failure happens on low voltage circuit breaker, which you can see is the operating mechanisms as well as the overcurrent trip elements of the breaker. So obviously really important that we make sure that not only the circuit breaker is in good condition, but also the settings, right, in case we can change those in the breaker we're testing, are programmed correctly. So what do we use for the measurements? As I mentioned before, right, on low voltage circuit breakers, we use primary injection. So what primary injection? I already mentioned, right, it will be the only method that we can use to test and verify the functionality of these type of breakers, as when we use this technique, we'll be able to test all the elements of the circuit breaker, the operating mechanism, the main contacts, the arc chutes or the D-ion chamber, right, to extinguish the arc, the trip unit, and the terminal connection. So everything is involved while we perform this type of test, primary injection. And how do we do it? Well, as the name implies, we need a primary injection unit, a unit that will be capable of injecting current through the conductors of the circuit breaker. As you can see in the example diagram that I'm showing, we'll be testing pole by pole in the case of a three-phase circuit breaker. So we're going to inject current, and the name also tells us that we're going to be using current levels equal to those that we expect to see in the field, so hence the name primary injection, right? As I mentioned, we're going to focus today on the SPI 225. I also wanted to show that we offered a very wide portfolio of primary injection units. I'm only showing actually in the slide only a few of the available instruments, right? So as you can see, we go from units that can deliver up to about 1,000 amps and going all the way up to 60,000 amps, right, for medium, low and medium voltage breakers with higher nominal currents. Again, we're going to focus on the SPI 225, which can give us up to 2,000 amps for instantaneous testing. And as I mentioned, you can see is part of the new generation of primary injection units from Megger. Before we dive deep into the specifics of the unit, the features, again, the advantages, and how it makes field testing easier, let's discuss the field challenges, right? To understand better the features of the SPI 225. So the first challenge we encounter when we need to perform these tests in the field is how we're going to power the instrument, in this case the SPI, right? The power obviously can come from the building circuits if we have those available, if we have power in the building that we're performing the test. If not, we need to look at either a generator or an inverter, right? Here we have to be really careful, right? The quality of the generator, the output of the generator or the inverter will affect the quality of the output of the SPI. We also need to make sure that we have enough power from either a generator or an inverter to comply with the specifications of the SPI 225. So that's the power. Then we need to look at the breaker configuration. Again, we're focusing on low voltage circuit breaker, not on power circuit breaker, this is more important, but not to be overlooked, right? First of all, the connection method, if it's either top feed or bottom feed. The classification and construction, right? Is it a molded case? Is it a power circuit breaker? And the features that the circuit breaker might have, right? Especially with the power circuit breakers, if I have in thermal memory, any selective interlocking that I have to maybe disable with the elements provided by the manufacturer of the breaker. If I have an under voltage coil, if that needs to be energized so I can test, and if there is any maintenance switch that has to be on or off during my testing, right? And the trip units as well, if I do need any external power, or the secondary injection tester. Again, those are typically provided by the manufacturer of the breaker. So I have to know what type of circuit breaker I will be dealing with when I go out in the field and perform these measurements. Next is the decision between using bus or cabling for my connections from the SPI to the breaker under test, right? Either or can be utilized. The current will be the main requirement that will dictate the best application for either option. Because this presentation is focused on low voltage circuit breakers, I would say with currents up to 2,000 amps, you can say the cables are the preferred method because of the flexibility and ease of connection. The length is of equal importance to thickness of the conductors we use, right? We want to minimize the impedance, the total impedance of the circuit we are connecting to the SPI, as this will obviously impact how much current we can get out of the unit in that particular configuration. We mentioned that it's important in this case, right, to look at the recommendations from the standards. In this case, the name NEMA AB4 that tells us that for these type of tests, the connections to each pole of the breaker should be made by copper conductors no less than 4 feet in length, right? And they even gives us recommendations for the size. They have a table that, depending on the rated current for the breaker, they will recommend a size for the cables or the conductors to be used. So that's a good table to look at again to determine the right size or gauge that I need for my test. Again, the idea or the objective, right, when we talk about connections is to minimize the impedance. So some of the recommendations that can give you to minimize that impedance, and again, especially when testing towards the limits of, in this case, what the SPI can give, which is 2000 amps, there are certain things we can do to, again, get the most current possible, the highest current possible. First, we can use conductors in parallel, 2 or more cables in parallel. The shorter the cable, the best, right? Again, to minimize the impedance, as well as increasing the gauge, or in other words, using thicker conductors. We also need to avoid loops, especially when using long cables, such as the picture you're looking at right now. This configuration, it might seem strange, right, for those that don't have a lot of experience, but this is a picture taken when the SPI was being used to test the ground fault protection element on a medium voltage circuit breaker, right, which by standard we can do with up to 1200 amps of current. So that's why we can use the SPI, and hence the long cables. And you see the cables are twisted, right? That's another of the recommendations to minimize the impedance of that circuit we connect to the SPI, and again, maximize the current that the unit will be able to inject, right? And finally, well, the connections themselves, right? Make them as good as possible. If you can, use bolted connections or clamps are a good practice as well, right? So that's the recommendation on connections. Now let's look at the Megger SPI 225, right? What are the main features of the unit that again will help me with these challenges that we just discussed? I will start by saying the unit is the smallest primary injection unit in its class, right? Judging by the output, the capability in terms of the current that it can deliver is a small and light unit. Once again, the unit can deliver up to 2000 amps of short circuit current. And most importantly, the current regulation is automatic, right? For those that have performed these tests in the field, you know that we face a phenomenon called current decay, right? So first of all, when we make our first measurement on a circuit breaker, we have to determine the peak of value, right? Let's say we need 700 amps. So in a traditional instrument, we have to find that point in the adjustment of the output where the unit will deliver the 700 amps for that particular configuration, right, with the impedance that I'm connecting to the instrument. So I start my test, especially when I'm testing, overload and those long time delays. The current will be injected for several seconds. And given the nature of the test itself, we were using high current. We're going to heat not only the circuit breaker, right, the conductor elements in the circuit breaker, but also the leads that I'm using for the test. So we will see something like I'm just showing you right now, that curve depicting the current, right? So the current will decrease since we are heating the conductors, and again, including the cable, the test cables, as well as the breaker under test. So this is something that always happens. So the SPI will always or constantly check or measure the impedance in the measuring circuit, right, while it is testing. So it will guarantee a constant current for the test, and thus giving me more accurate results for those injections that take several seconds. Next is DC offset, which again is something that we have to be very careful, right? Traditional units will have to go into the settings and adjust, for example, the firing angles, so we can ensure that we don't see this type of behavior, right? Having a DC offset, a DC component that will cause that, especially for those tests where we're measuring instantaneous trips, that the breaker will trip, seeing a higher current in those first few cycles, right? So again, the SPI, the algorithms, the electronics in the SPI will make sure that you don't have that issue. So I can guarantee constant current in the output. In terms of the output, whenever you need higher than 2000 amps, the SPI will be capable of using more units either in series to increase the voltage in the output or in parallel to increase the current capability. Right? The system can DC chain up to 4 units together. And I'm showing you here a table as an example, right? Data taken using an 800 amp breaker. And you can see that with 4 units, right, using 120 volt source, you can achieve close to 7,500 amps, again, using 4 units. If you're using a 240 volt source, you can achieve close to 7,900 amps. And also notice, right, what we were discussing before when we talk about the leads, the impedance that we connect to the output of the system, going from 2 feet to 10 feet, obviously we will have an impact on the maximum current that we can achieve. But again, the capability of the AC chaining units together is also great. That way you have a modular system that you can configure and adjust based on the needs or the breakers that you're testing in a particular day. The next is the software. For those that are familiar with our instruments, we use the flagship software PowerDB, which we use not only for SPI, but for many other instruments in our lineup. And you can see from what I've shown you already of the unit itself, it hardly has any buttons. It actually only has one button, which is the emergency stop button in the front, right here. Other than that, is just connections to either the computer or the smart touch view interface, the SPI, that can be used as well. A USB port to connect to the computer as well, and then connections to my specimen, right? My output, my tabs, which we'll cover in a minute, as well as a binary input if we want to monitor an extra contact. Again, PowerDB will be the software to control and generate reports with the SPI 225 system. Either if you are using the computer or the SPI, the software looks and behaves exactly the same. Features are the same. No differences at all between the SPI or the computer running PowerDB, which is great. So that means less training and again, learning only one software. And you will see the software is really, really easy to use. I will show you that towards the end of the presentation. Another great feature of the software is the inclusion of a very large, right now, up to close to 7,000 curves available, right? Those time current curves for the circuit breakers. So I can just go into the library, select the breaker that I'm testing, and the software already has the TCC baked in, not only to display it, but also to plot the results inside the curve and immediately give you a pass and fail result. I'll show you that as well when we go over PowerDB testing. Right? When I finish my results, my measurements, I get my results. The software will automatically generate a report. Right? Just showing you an example. We're going to look at this also in detail in a few slides. So now we know, right, what are those challenges and how the SPI can help me overcome those challenges. What are the features that will help me overcome or make the testing not only easier, but also more accurate and faster, right, more efficient in the field. So let's go now into the steps of testing a low voltage breaker with this unit. And let's go back to discuss connections, right? We mentioned that the unit has different tabs to connect, right? The first one is the 25 amp 70 volts maximum tap, right, which is located in the front panel of the instrument, is this connection right here. Typically, if you're using this tab, you can use the sleeve test leads, which we include with the unit, right, with alligator clips. And these test connections are excellent for terminal screws and pins where the spade lugs cannot be used, right, for small breakers and obviously when not using higher currents, right. Next, if we go look at the side of the instrument, we have the two remaining tabs, right? As you can see, we have a common connection, which is displayed in the bottom, right? So we will use this common for either the 125 amps tab or the 500 amps with displayed in the upper part. Something to highlight, and it's very, very important when using the SPI, is that we only gonna wire one tab at a time. Even if we're not using it, we cannot wire two tabs simultaneously. Well, the unit will not work that way again. So very important, you only wire one tab at a time. So when using the 125 amps tab, these two leads can be used, right? The common with the 4 odd current lead shown in the middle of the slide, and the tab itself with the AWG number 6. Both are showing on the circuit breaker side, you see that adapter, right? Now going into the 500 amps tab, well, you can use both the 4 odd leads to use again the 500 amps tab. Notice that the voltages, right, the maximum voltage or the compliance voltage that I can get on each tab is lower as the current increases, right? So it's very important that you select the proper tab. That's the reason the unit has tabs and not only one output connection, right? So if you don't need to achieve higher currents, then you can again select the tab accordingly, as you have a higher compliant voltage and thus the unit being able to inject the current. Another very important highlight, right, as I mentioned in the beginning, the unit can give you up to 2000 amps, right, but the tab, the maximum is rated 500 amps, and as just said, that is the rated current, and so that's continuous rating. So all the tabs in the unit can be overloaded up to 4 times its rated value, hence the maximum 2000 amps available for short circuit test. Okay, so going back into the connections, right, again I mentioned that adapter that we have at the end of the lead on the breaker side, so we cannot connect directly to a breaker with that adapter, right? So we shipped several accessories to connect to the breakers, starting with high current alligator clamps, both 175 amps, and also high current probes in 3 different sizes, right, for those breakers with spade lugs. So you're gonna use these adapters to connect directly to that, these accessories to connect to that adapter in the lead. Connections are summarized in the top overlay of the top panel of the unit. I will reiterate, really important that you only wire one tab at a time, right? So the front connection, you have your common and the 25 amp tab, and on the side you have one common and then your two tabs, 125, which is the round connector, and the 500 amps, which is the plate. Okay, so that's connections. Then, so we assume, okay, we're connected to the first pole on the breaker. What are we going to measure? And for that, we can look at the well-known time current curve, right? And again, for us to have a level ground and understand what we're measuring, let's review a little bit of what this curve is describing. So it will actually tell me the performance of the breaker that I'm testing, right? And we can divide, or we can highlight 2 important sections of the curve. The first one is overload, that it will tell us how the breaker will behave when there is an overload. And as you can see, I have two internal sections in this overload part, right? First of all, the short time, right? The purpose of the short time setting, or that section of the performance of the breaker, is to allow time-based delay to elapse before tripping the circuit breaker for moderate current faults. Right? Example of these types of overcurrents will be for the inrush on a large motor starting, or for example, a transformer inrush when it's first energized. Right? So again, this allows those motor faults to clear before deciding to trip the circuit, or before the circuit breaker trips, right? And then we have the long time on the upper section right here. The purpose of this setting is in the same sense, to allow a time-based delay to elapse before tripping, now for low-level current faults. Right? Examples of these types of overcurrents would be overloading of a power transformer or a large motor for a few minutes. Again, just giving time for those low-level current faults to clear before the circuit breaker trips. And conversely, right, when there is a short circuit in the system, then we don't need to delay the tripping, and that's when we go to the instantaneous pickup or instantaneous testing of the circuit breaker, right? So it will be only a few cycles before the circuit breaker will trip. So those are the two main sections that we're going to be able to test on these type of circuit breakers. So when we're testing the overload section, right, when we test the overload elements of the circuit breaker, in reality, physically, we're testing the thermal protection of my circuit breaker, right, highlighted here in yellow. And we look at the instantaneous part of the curve, we're going to measure the performance of the magnetic protection of my circuit breaker, right? We typically call these circuit breakers thermomagnetic, right? So again, those two sections are described in the time current curve that we just discussed. So let's go into the testing itself. And so now, assuming we have our connections made to the first pole of the breaker, first we need to set up our DB. And again, as I mentioned before, there is a circuit breaker library, right? So we need to select the breaker we are going to test. So we're going to click on circuit breaker curve library, say manufacturer specific, and choose between molded case and airframe. I tell the software the manufacturer. I'm going to use a Square D as an example from the FH family, 90 amps, rating of 90 amps. Accept my selection, and the software will show me the curve, right? I can see that I have both long time and instantaneous testing, so no short time for this breaker. Notice also the frame size is already indicated, right? Because I selected the breaker from my library. Before we dive into the testing itself, I want to show you another section of the software, which is the nameplate, right? If you click this button right here, the blue icon in the top, you will get presented with the screen. So you can fill out identification information, right? Important, so your report looks better and you have all the identifications both for the breaker under test as well as the conditions, right? The location, even temperature, humidity, the name of the person running the test, if you have a job number, and so on and so forth. Like these will be part of your report. So it will take you a couple of minutes to fill out. And then we can go into the measurements themselves. We're gonna start with the long time test, okay? And again, notice that the frame size is selected. The test current is also already filled out automatically, which is 3 times my rated current. I'm gonna start with phase A. This screen is for me to review the settings, right? The test current itself, the tap verification, which the unit will use to detect the tap connected, as well as to measure the impedance of the output circuit to adjust, and give exactly, in this case, 270 amps. So verifying connection, again, is finding the tab, calculating the impedance, and then running the test. Notice in the graph I have live results, right? So that I have that red arrow representing the time, right? The current that I'm using and the time. Full disclosures, I made this video using simulation mode, so I will be simulating the trips of the breaker. So notice, as soon as the breaker trips, the software will plot the result in the curve itself, right? So I will have live values in the curve, so no more comparing with a piece of paper and then guessing exactly where my result will fall in the curve. So switching to phase C, obviously we have to switch connections to that phase. And again, looking at live results, I have a timer in green in the upper section of the screen. I have a live view of the current as well as the input voltage on the left. Okay. On this case, I wanted to show you a fail measurement, how that looks in the graph. And I'm going to leave it like that for a minute, and then switching to phase B. Same process. The unit will always need to determine which tab is in use, calculate the impedance, right? Because we changed connections. So again, showing live results. And again, I'm going to trip this portion or this phase when it's within the limits established by the curve. So you notice it turns green when it goes inside the limits. And let's say that, okay, our phase C failed. So let's say we change the settings or we do some maintenance on the breaker, and notice that there is an as left column, as found and as left, right? So I can rerun my test on the as left, right? After I did either some maintenance procedures, corrections, or change the settings of the circuit breaker. And I will be able to retest that phase while keeping my as found result, in this case a failed result. It's important to have that in the report. So I'm going to do past test on this case, phase C. So again, I don't erase my as found or my previous measurement. It's still in my report, but I can retest the phase if I did a change or some type of maintenance in the breaker. Okay. So that is the long time test. Let's go now to the instantaneous. Pretty similar, right? We switch to this screen, right? Looking at the instantaneous, same thing. We have now our current will be 900 amps, right? Automatically selected by the software using 10 times the rated current of the breaker under test. So let's go ahead and run the first measurement on phase A. And same process, the unit will have to determine what tab is in use, determine the impedance, and start testing. Now, different from the long time test, right now our arrow will be horizontal as the unit is doing pulses. If you pay attention to the current indicator, the current is slightly going up each cycle. Also the time, you see, it looks like it doesn't change because the unit again is doing pulses. You can change that in the settings. I was using 5 cycles on, 100 cycles off. So again, the unit will keep doing those pulses until the breaker trips, right? So that's why you see the horizontal line, and you can see that it's slightly increasing. And you can see also in the yellow current indicator how the current is doing in steps of 20. You can also change that step configuration in the settings, right? So testing phase B now. And we're gonna make that B phase fail. I wanna show you how that looks in the report, right? So A and B, good, they trip within the limits of the curve. B phase, it's a fail, right? It's a red result. So how does that look in the report? To generate the report, it's as easy as to click this icon right here. So let's look at how that looks in the software, right? When clicking live, just a couple of seconds, the report is generated. Includes my identification that I filled out in the nameplate, the graph with the curve, again, so no more comparing with paper, and my numerical data in the table, highlighting the ones that failed, and I have that big indication in the top saying that something went wrong, something failed. So I go back to the testing screen. Let's say again, we did some maintenance, some change in settings maybe, and let's retest phase B. And now we're gonna trip that breaker inside the limits of the curve. So how will that look in the report? So doing the pulses, increasing 20 amps each time. Look at the time is 5 cycles per pulse. It trips, and now it passed. Right? So my 3 phases pass. My previous as found results still in my report, but now the indication is that all tests pass are within the limits established in the TCC curve. So now it only rests to save my file as either as a PDF or as a native PowerDB file, which is a PDV XML, in case I need to retest this circuit breaker in the future, or if I need to test a similar breaker, I can make a copy, change the identification data, and rerun my measurements. So that's all I have. I'll turn it over back to Mike for questions and contact information.
All right, thank you, Daniel. So as stated, the presentation portion of our webinar has officially concluded. We'll now take some time to answer as many of your questions as possible. For those of you who are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be sent to all attendees in about 2 business days. You can also view video recordings of previous webinars, as well as register for our upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar, You Ask, We Answer, a panel discussion on battery testing. All right, let's get into some questions. Our first one I'm going to send over to Volney. Volney, is a LVPCB or MCCB rated for a fixed number of operations in its life? How does the primary injection test count in that regard?
Okay, Michael. So the question is asking about the extension of the life of the breaker in the sense of the operations of the breaker. This is more like a spec from the manufacturer. They might have some values in the specs. However, one aspect that I want to point out on regards to testing is about the second question, or the second part of the question. How does the primary injection test count in that regard? One thing that it's important when testing circuit breakers for the instantaneous current is to do it accordingly to the curve and the procedure that Daniel explained, like doing the injection impulses and starting from a low value, and never to exceed the short circuit rating of the breaker. So the breakers will have a certain spec in relation to the short circuit rating, and well, that is kind of the mechanical strength of the breaker, and if it is not guaranteed that it will not fail if you inject a current higher than that. So just one of the limits or the limitations or the things that you should consider when testing breakers: never to exceed that amount of current. In some breakers, it might be too high that with the instrument that you're using, you may not exceed that, but in some cases, you could have a powerful instrument that exceeds the ratings for breakers, especially with those molded circuit breakers, molded case circuit breakers that might have a low short circuit feature. So that's mainly what I wanted to point out, that you can deteriorate the breaker if you exceed those currents.
All right, thank you. Sanket, could you please shed some light on the pros and cons of primary versus secondary injection?
Yeah, so primary injection is where you actually inject current through the breaker, whereas secondary injection testing is another form of testing where the signals are fed to the trip unit without actually injecting current through the breaker. Now there are pros to using a secondary injection where you do not need let's say you're testing a really big power circuit breaker. You do not need a high current test set for that. For secondary injection testing on that circuit breaker, you can just get a small secondary injection unit and carry out secondary injection testing on that. Which is kind of not the case when we talk about units like the SPI, which are used for testing on really small MCCBs, where the SPI is a pretty portable unit. It's a small unit, so you don't have to worry about that. But when we talk about really big circuit breakers, sometimes people do go for secondary injection testing, but we need to realize that when we do a primary injection testing, we are actually carrying out a complete test of the circuit breaker. Right? So definitely primary injection testing tests the whole system rather than just the brain of the circuit breaker. And so it's more advantageous to do a primary injection testing instead of secondary injection testing. When you do a secondary injection testing, you're just checking out the trip unit logic of the breaker, but you're not checking the other parts of the breaker. You're not checking the operating mechanism. You're not checking the current sensors. So you're not doing a complete test of the breaker. But when you do a primary injection testing, all of those things get checked out. So it's a more complete test compared to the secondary injection. So some people do go for secondary injection testing just because of the comfort aspect of it, and this applies while testing really big circuit breakers. But then primary injection testing is kind of a better test to carry out on your breaker than secondary injection testing.
Thanks, Sanket. And while I have you, I'll send you the next question as well. And that is the standard okay with testing all three phases at once by putting phase A, B, and C in series and only breaking them out if you have a failure on one of the series?
So since we're talking about the SPI here, I will go with what NEMA AB4 says, and that's the document that deals with testing of molded case circuit breakers used in industrial and commercial applications. So what it says is that if your breaker does not have an electronic trip unit which incorporates ground fault protection, then in that case, each poles need to be tested individually. So it depends on whether your breaker has ground fault protection, which is typically not the case when you talk about MCCBs. They do not typically have a ground fault protection. So you will end up testing individual poles while testing MCCBs. If you do run into a breaker which has ground fault protection in it, then in that case, you will need to connect two poles in series with each other to be able to overcome the ground fault protection and be able to test the other elements.
All right, thanks. So Daniel, how do you test if the breaker curve is not there in the software?
Okay, that's a good question. I meant to explain that during the presentation. I skipped it. So as I mentioned, you do have a large library, but by no means we can claim that we have all breakers, right? So if you do have a breaker that is not in the library, the immediate option that you have is that you use the generic breaker option in the software. So that will allow you to just define a frame size, and then also for you as the user to directly type the test currents that you're going to use for that test. The other option is that if you do have that curve in paper, right, for the breaker you were testing, you can contact us, right, and if you can share a PDF or a scan of that TCC curve, again, we'll digitize it and it will send you back a file that you can import, so that you will have that in the library. So again, the immediate answer is to use the generic option of the software. And if you test that type of breaker frequently, you need it in the library, we can add it if you can share a PDF or a scan of the curve.
Thank you, Daniel. Sanket, what is the biggest breaker that can be tested by one SPI unit?
So the reason why the SPI is called the SPI 225 is because what we say is the biggest breaker that can be tested with the SPI is a 225 amp rated breaker. Now the logic behind that is the maximum current that the SPI is capable of putting out is 2000 amps, and that's, again, when it comes to these high current tests, you have to note that the currents that are provided on the data sheets are based on perfect conditions, based on short circuit conditions, right? So on paper, let's say it's 2000 amps, and when you do an instantaneous test, a typical instantaneous pickup is 8 times the rated current. So if you take a 225 amp breaker multiplied by 8, the current that you get is 2000 amps. And that's the logic behind saying that we can test a 225 amp breaker. Now, of course, when you test, you can lower the instantaneous settings to a lower multiple, and so you can. It is possible to test bigger breakers if you cannot achieve 2000 amps or for whatever reason. And you have to know that the 2000 amp limit is also an instantaneous current, which means that you cannot continuously put out whatever the maximum current is for a long duration. So it is based on instantaneous testing. So yeah, the answer is 225 amp breaker is the biggest breaker that can be tested with the SPI.
Thanks, Sanket. Daniel, can SPI be used for ground fault testing as per NEC 230.95?
Oh, great question. And the short answer is yes, absolutely. As the person that sent this question, right? As per that clause in the National Electric Code, right? These particular tests, right? When you want to assess the condition of that element, that protection in the breaker, the current that you will use depends on the rating on the breaker. But when the circuit breaker is rated 1200 amps or above, that is the limit for this test, right? So any breaker that doesn't matter the rating, if it's above 1200 amps, you're gonna test the ground fault protection element with 1200 amps. So as Sanket just explained again, the maximum current of the SPI is 2000 amps. A few seconds, you certainly can use it for ground fault protection testing. And that's actually the picture that I had in the presentation, which, by the way, you're gonna get along with the certificate. It was actually testing that particular element. So yes, you can use the SPI for that application.
All right, thank you, Daniel. Volney, other than breakers, what else can I use the SPI 225 for?
Okay, so the SPI is a unit that injects AC current and as per the limits or the maximum currents that it can inject. If you use it on continuous mode, uh, you can inject current for 30 minutes on each tab. The 100% of the tab you can inject for 30 minutes continuously, and instantaneously you can use it for 7 seconds as one of the limits on the that Sanket was mentioning before. So if you have an application that you need to do a constant current injection of AC, you can leave the unit in manual mode, injecting current constantly through a bus bar, for example, and you are reading the meters and the relays displays to do like an actual primary injection test or verification without tripping anything. So you could use it for that. Also, we have fuse manufacturers that they test design design testing of the fuses with this type of instrument. So if you while you are within the limits of the unit, you can use it for fuse testing as well. And there's some reclosers that are called trip savers. Those are also possible to be tested with this instrument.
All right, thank you, Volney. Sanket, how long can you push 2,000 amps?
So as per the data sheet, we can push 2000 amps for a period of 7 seconds. You have to understand this is the way these test sets work. The lower the current, the longer you can push it through the circuit. But as the current becomes higher, the load increases obviously, and the test set cannot put out that high load can only put out that high load for a limited amount of time. So you have to pay attention to these things while testing circuit breakers. Look at the data sheet, see what is the duration, and based on that, select an appropriate tab. Just be aware of the limitations of the test set while purchasing a test set or while using it.
All right, thank you. Volney, can we use this equipment to measure the contact resistance, bus bar resistance as well?
Okay, that's another interesting application. When you do current injection, definitely you can measure resistance. However, this instrument doesn't for the measurement of the contact resistance or the bus bar resistance. In addition to injecting the current, you need to measure the voltage drop, millivolt drop that you get across the resistance that you are interested to measure. Contact resistance instruments, they will have the means to do these. They will inject current, measure and measure the voltage drop, and they will calculate the resistance. The SPI, it can inject the current, but it doesn't have any means to measure the voltage drop across the terminals of the resistance. So if you need an accurate measurement and it has to be a DC current, a DC resistance measurement, it's better to use a different instrument. However, if you are injecting current, let's say like in a permanent or a continuous mode, you're injecting some current through a connection, and you have a voltmeter, you can measure that voltage drop through the contact, and you can calculate the resistance. It's like a quick and easy way to measure a resistance. However, it won't be reported into the form because the instrument is not doing it directly. And one more thing that I just remember, in the report, usually when you do contact resistance on when you test breakers, you do the contact resistance test. So the report has means to include those values But the idea is that you will type in those values from a result that you obtain or using another instrument. So just a side comment about the contact resistance, that you can include that in the table or the report.
All right, thank you, Volney. Daniel, do you need to wait between phases to allow for thermal heating?
Okay, certainly. As we covered, right, especially when you're testing the overload elements, right, your thermal elements of the breaker. I mean, that gives you a hint that when you are injecting the current, right, you're again testing the thermal elements of the circuit breaker. And certainly you can make this exercise, right, where you, let's say if you test phase A in the breaker and you do a long time test, you're going to inject the current for certainly for a few seconds. And if you immediately test phase B, you might not get the side or even close tripping times for that phase. And again, this has to do with the thermal characteristics, right? In other words, the elements are now heated, so they will perform differently, right? We all have gone through testing and then we want to reset it. The breaker is not resetting, it's just the temperature is too high. When we went through the testing, might have been probably too quick for the presentation, but did you notice that when we tested those over loading elements, we tested phase A. A common recommendation is you test the phase that is far from phase A, which in this case is phase C, and then you go back to phase B. But certainly recommended for you to wait a few minutes, right, to let the elements cool off between those measurements. Again, especially important when testing the overload, long time, short time elements of the circuit breaker.
Thanks, Daniel. And while I have you, the next question is also for you. A circuit breaker manufacturer has told me they do not want primary injection testing and prefer primary verification testing. Do you have an opinion on this?
Well, certainly, this is a very interesting question, something that, I mean, it's up for discussion, right? And I will start by saying I'm not exactly sure what we mean by primary verification testing, or what would be the difference, but I mean, we are aware, right, that we have other methods. I mean, I think it was the first or second question that Sanket answered about secondary injection. We know a lot of circuit breaker manufacturers offer these secondary injection units that will help you make sure that the trip units are working correctly. But if we go back, to the definition of primary injection, and if we look at how the test is performed, right? This is the method that closely or pretty much is the same as the conditions that the breaker will face or that will be under when in service, right, in the field, right? So we are using the same level of current again as the expected or the rated fall values for the breaker. So when you inject the current, you're testing the whole system just as if it was in service. When you perform secondary injection, you're just doing some sort of a simulation or going through that secondary part of the circuit breaker, the secondary circuits, just the measuring part, but you're skipping, the main contacts, the main means of the breaker that will be used during service, right, in field conditions. So again, certainly up for discussion. You have advantages of one method over the other. On the one hand, right, you can argue the secondary injection units are for sure smaller, we can say more portable, lighter, right? Yes, because those units won't be able to have these higher currents that are needed to test the circuit breaker.
I'll
All
add
right,
to that a little bit.
Sure.
So I guess what primary verification means is that you verify the primary by injecting a lower current. along with, of course, testing the trip unit logic by using a secondary injection test set. So when you do a primary verification, you verify the circuit of the circuit through which the current flows, but you also need another test set, which is a secondary injection test set, to check the trip unit logic. And I agree with what Daniel said. When you do a primary injection testing, you come closest. You put the breaker through exactly what it would face if a fault were to occur. The exact current that would flow, and what would happen if that current were to flow. How would the trip unit act, and how would the other parts of the system act? So that's why we say that primary injection testing is a complete test. It's a true test. Yes, it does require big test sets for testing bigger breakers, but it is a complete test.
All right, good deal. So it looks like that's all the time we have for our Q&A session today. We apologize if we didn't get to your question today. We had a lot of really good ones come in. We just don't have the time in it for our schedule today. We'll be following up with you offline in the following weeks. As a reminder, a copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you have a great week.